For decades, physicists built the Standard Model, a towering framework describing fundamental particles and forces. It explained the universe's building blocks with incredible precision, but a crucial piece was missing. Why do fundamental particles, like electrons and quarks, or the force carriers of the weak interaction, the W and Z bosons, have mass? The elegant equations of the Standard Model seem to require them to be massless. The issue traced back to the fundamental principle of gauge invariance, a mathematical symmetry central to quantum field theory. This symmetry successfully described forces like electromagnetism, predicting massless photons. Applying it to the weak force, or the unified electroweak interaction, demanded its force carriers, the W and Z bosons, also be massless. But experiments showed these bosons possessed significant mass, a direct conflict that stumped physicists. Adding to the puzzle, attempts to build a gauge-invariant theory that allowed for massive W and Z bosons often predicted the existence of extra massless particles known as Goldstone bosons. These particles were simply not observed in experiments. Physicists faced a dilemma. They could abandon gauge invariance, which worked so well elsewhere, or they could find a way for particles to gain mass without violating the symmetry or producing unwanted massless particles. The key insight arrived from an unexpected corner: condensed matter physics. In the late 1950s, physicist Yoichiro Nambu recognized that spontaneous symmetry breaking, where a system starts symmetric but ends up in an asymmetric state, could occur. In 1962, Philip Anderson, an expert in superconductivity, saw a parallel. Superconductivity involves a phenomenon where the electromagnetic field effectively becomes short-ranged, even though the underlying theory describes massless photons. Anderson suggested this same kind of spontaneous symmetry breaking might be at play in particle physics, potentially giving mass to bosons, while avoiding Goldstone bosons, which might be absorbed in the process. Inspired by these ideas, several teams independently published papers in 1964, exploring how this mechanism could work in relativistic quantum field theories. 3 papers published in Physical Review Letters that year, by Robert Brout and François Englert, by Peter Higgs, and by Gerald Guralnick, Carl Hagen, and Tom Kibble, showed that if a specific type of field existed throughout the universe, it could break electroweak symmetry. This field, unlike any other known, would possess a non-zero value everywhere, even in otherwise empty space, a state often depicted by the sombrero potential shape. This constant, non-zero value allows the W and Z bosons to acquire mass. This proposed field became known as the Higgs field. It's a scalar field, meaning it has no direction in space, unlike the fields associated with forces like electromagnetism. Its peculiar property is that its lowest energy state isn't zero, but a non-zero value. This vacuum expectation value, as it's called, is what permeates the universe. As particles interact with this field, they effectively gain mass. The more strongly a particle interacts, the more mass it acquires. The field itself, when excited, would manifest as a particle. This particle, predicted by the theory and necessary to prove the existence of the Higgs field, was the Higgs boson. The Standard Model predicted it would be a massive scalar boson with zero spin, even parity, and no electric or color charge. It would also be highly unstable, decaying almost instantly after being produced. Finding this elusive particle became the central problem in particle physics for decades. The experimental hunt required unprecedented technology. Particle colliders needed to reach energies high enough to produce the predicted particle. Detecting its fleeting existence and its decay products, especially against the overwhelming background of other particle interactions, demanded highly sophisticated detectors and immense computing power. This effort took over 30 years and led to the construction of one of the most ambitious scientific instruments ever built, the Large Hadron Collider, or LHC, at CERN. The LHC, housed in a 27-kilometer tunnel, was designed to collide protons at energies far exceeding previous colliders. The sheer volume of data generated was staggering, requiring a worldwide computing grid to analyze trillions of collisions. Physicists meticulously searched through this data, looking for the unique decay signatures predicted for the Higgs boson. The tension built for years. Then, on July 4, 2012, the ATLAS and CMS experiments at the LHC announced they had independently discovered a new particle. Its mass was measured at around 125 GeV per c squared, falling squarely within the predicted range for the Higgs boson. The statistical significance of the findings was overwhelming, exceeding the 5 sigma threshold required for a formal discovery. The particle was undeniably real. Initial observations showed the new particle behaved in ways remarkably consistent with the Standard Model's predictions for a Higgs boson. Further analysis confirmed its properties: zero spin and even parity. These are fundamental characteristics expected of a Higgs boson. This also made it the first elementary scalar particle ever discovered in nature. By March 2013, CERN formally confirmed the existence of the Higgs boson, providing strong support for the concept of the Higgs field permeating space. The discovery held immense significance. It validated the Standard Model's mechanism for generating mass, a cornerstone of particle physics. It explained why the weak force has its incredibly short range. Crucially, it confirmed the existence of a fundamental scalar field, a type of field previously only hypothesized, opening the door to explore other theoretical scalar fields potentially involved in phenomena like cosmic inflation. While often simplified as the particle that gives mass to everything, the reality is more nuanced. The Higgs field provides rest mass to elementary particles like quarks and leptons through a mechanism called Yukawa coupling, and to the W and Z bosons through the Higgs mechanism. However, most of the mass of composite particles like protons and neutrons comes from the strong nuclear force binding energy, not the Higgs field. The Higgs field doesn't create mass, but rather gives fundamental particles their intrinsic mass based on how they interact with it. The discovery also has potential implications for cosmology. The measured masses of the Higgs boson and the top quark suggest that the vacuum state of our universe might be metastable, like balancing a pencil on its tip. While stable for billions of years, a quantum fluctuation could theoretically trigger a transition to a lower energy state, potentially changing the fundamental laws of physics and altering or destroying the structures we observe. This remains a theoretical possibility, highlighting how interwoven the microscopic world of particles is with the vastness of the cosmos. The Standard Model leaves the Higgs boson's exact mass as a parameter to be measured, not predicted, which is seen as theoretically unsatisfying. Furthermore, interactions with virtual particles should, theoretically, give the Higgs an enormous mass, far exceeding the observed 125 GeV per c squared. The fact that it's so light points to the hierarchy problem, suggesting there might be unknown physics beyond the Standard Model keeping its mass in check. This puzzle continues to drive research. Within the theoretical framework, the Higgs field in the Standard Model is described as a scalar tachyonic field. This term tachyonic refers to having imaginary mass, not moving faster than light. It simply indicates an instability in the field's potential that causes it to settle into a non-zero ground state, breaking the symmetry and leading to the Higgs mechanism. The Higgs boson itself, however, has real positive mass. Producing a Higgs boson in a particle collider is a rare event, like finding a specific grain of sand on a vast beach of collisions. At the LHC, it happens in only about 1 in 10 billion collisions. Once produced, the Higgs boson decays almost immediately into other particles, with a mean lifetime around 1.56 times 10 to the power of minus 22 seconds. Physicists detect it by reconstructing these decay products, looking for specific patterns, like pairs of photons or Z bosons, that match the Standard Model's predictions for Higgs decay. These patterns, or branching ratios, depend on the Higgs mass and are predicted precisely by the theory. Outside of physics circles, the Higgs boson is famously, or perhaps infamously, known as the God particle. This nickname originates from the title of a 1993 book by Nobel laureate Leon Lederman, The God Particle. Lederman, a key advocate for the superconducting supercollider, originally wanted to call it the God particle, due to its elusive nature and the expense of the search, but his publisher deemed it too controversial. The name stuck in the media, much to the dismay of many physicists, including Peter Higgs, who found it embarrassing and misleading. The nickname suggests the particle explains everything or reveals divine secrets, neither of which is true.